Welcome to the last lecture, Introduction to Cryptography. And today we will finish the area of bulletproofs. Okay, let's see. What do we need in order to understand bulletproofs? So first thing we need is the knowledge. What is a zero-knowledge proof? We had this on this slide. We have two parties. We have a prover, we have a verifier, and we want to show that we know a secret, and the verifier has to be convinced that this is true. We started with perfect zero-knowledge proofs, but now we are mostly talking about computational zero-knowledge, which means that the communication cannot be distinguished from random communication. So there is maybe some cryptographic structure, but in order to distinguish that, we have to solve a problem which we assume which is hard. We already manipulated the group so that we can do modular operations on the base and in the exponent. In the base, it will always be P, and the exponent, it will always be Q. That is a trick that we have already introduced. And the interesting thing is a very nice breakthrough was by Schnorr when he came up with his proof, which was not perfect zero knowledge for any verifier, but it is a perfect zero knowledge for an honest verifier, where we prove that we know an exponent x. And this is really the foundation of everything which comes later on, in order to prove that this is the case, because this was the first, not the first sigma, but this is called a sigma protocol, because what you have is you send some commitment to some random number A, then you get a challenge C, and then in the end you send an exponent B, which is dangerous, but it's not dangerous because you have here this random commitment to R, which produces a random output here. So this was, and you can reconstruct that. You can make this protocol if backwards, because you know B, and then you can construct B in such a way that it always fit. So this is called sigma protocol because this communication structure looks like a sigma. Okay, so this is probably the C, and this is the A, and this is the B, and I don't know what this is. Maybe this is the Y or something. I don't know. So that's why it's called. If you see this in literature, sigma protocol, it's just not because it's this letter, it's just because of shape. Okay, now the next trick is that we can always do, but we don't talk about this, is the Fiat-Charmy heuristic, that we can replace this interactive part of C with a hash function. So in last exercise, we have seen that this is tricky and you can make mistakes, and you should be sure that you have enough choices, but this makes the interactive zero-knowledge proof into a non-interactive zero proof. So basically, you can prepare anything on your own. You don't have to talk to somebody else. And so the prover can write down a proof, and the verifier can verify it later on at some point and see, okay, this all makes sense. So this was a Fiat-Charmy heuristic, and starting with that, we can do prove that logarithms are the same with this trick. We can do many more protocols which have always the same structure somehow. Here, this is important because what we use is basically we use the same commitment and the same challenge C for both of them, and we do the same calculations. And this is used in order to do proof of multiplication. A side note here, so I was re-editing this slide and found out that the proof I originally had was too complex. So it was too many checks. So this is just a subset of one, but this is still complete and sound and zero knowledge, because it is not necessary. So we prove that G is somehow related to G to the A. and we should prove that g to the b is g to the a times b, that this is basically multiplied. For this we use this, so this is multiplied with a, but it's not necessary to prove that g to the a is multiplied by b. We just need to prove that we know g to the b. So that means we have one check less for the verifier, and I think one commitment less. So that's something we can shorten this proof a little bit. And then we continued and found out that we could, first of all, we have to be careful about the generators, because if we know the relationship between the generators, we can cheat. And so we found out that we have to produce generators also by hash functions, which has to be agreed by everybody or as a standard, so that we don't know the exponents of the generators to each other. So which is called nothing up my sleeve, this technique. And then if we have that, we can commit to any vector of things in one number. So arbitrary information committed with one number. Not so surprising if you know what a hash function is, but in this case, you can prove that if a discrete logarithm assumption is true, that you can commit to anything in this function, and you can even commit it safely. So you can even commit to a vector of zeros and can prove that you know this vector of zeros. And for a very long time, this means, okay, so we have proofs for hidden algorithms and so on, and you have lots of operations. You can prove that you know a constant, you can prove that you know the addition of 2 bits, and if you have all this, and you can also prove the multiplication of 2 hidden things. So it was complicated. I also have reduced that to a smaller set. And so if you have these building blocks, then you could basically do anything. We started with permutation of 2 numbers. In the exercise on Thursday, we'll talk about permutation of 3 numbers, which is probably also fun. And because you can rewrite this as an arithmetic circuit. An arithmetic circuit consists of addition, multiplication, and constants. So you could have this circuit here somehow and produce some arithmetic circuit which, simulate a Boolean circuit with an arithmetic circuit is actually having something simpler simulated by something more complicated, but it works. And if you have Boolean circuits, then this proves that you can prove everything with a zero knowledge proof. So you have some hidden inputs, and you want to prove that there is some relationship between these hidden inputs. For example, somebody has 10 euros and he wants to give 5 euros to the other one, and the other one says, I have received this 5 euros and now I have new budget, and these are 3 hidden numbers. Then you can put this into Boolean circuit or directly as an arithmetic circuit, and every information is still hidden, but you commit to a hidden number, and some observer would say, yes, you did this right. So this is now perfectly right. I can check it, and I can check it with very extremely high probability that you have not cheated. So that was the state of the art until 2018, I would say, where you could say, we know that everything can be proven with a zero knowledge proof, and we have these techniques, and the zero knowledge proofs are linear. So for each statement here, for each arithmetic circuit, you need a linear proof, and for each Boolean circuit, you need a linear constant number. So basically, you just have to build a Boolean circuit which is very small to build a zero knowledge proof. So fine, so good, because that's already surprising that you can prove everything. But then there was a breakthrough in the year 2018, and preceded by some other paper in 2017, where they decreased the complexity a lot, and especially the communication complexity and the round complexity. So here, round and communication complexity, you can reduce the round complexity by parallelizing it and making one big sigma proof. but the communication complexity would be still, for each arithmetic operation, you have a constant number of messages of thousands of bits of crypto code sent around as in elliptic curves or El-Jamal. So that's and this changed drastically without increasing the computation complexity. And the trick is so that we are now working with these hidden commitments, the same slide as you have seen before. And it's clear that we can prove this with linear complexity. But there is a bulletproof for this generalized commitment that works in logarithmic number of messages. And that was a surprise that this is possible, because in the beginning, so you still have this number. So you commit to some kind of U. You have this number. You have a vector of generators, which we don't have to publish because they're generated out of a hash function. But in this, it is a vector of information given. And the cool thing is that in this vector, you can work with that. And the trick was the following. I sat down and made a picture for that. So this is a vector that you commit to, and this is a vector of generators. So the idea is that you have a recursion where you go from this. So this vector, this has a length of n. So this is n, and this is also n. And you commit to a shorter vector which has this length of n half. So you taken two parts and added it. And in order to add them, so if you just add them, then this would be easy for a prover to cheat, because I know I will just add them. So I can actually have multiple versions of that. So we need some kind of interaction from the verifier, and the verifier will give us an alpha here. So the verifier chooses an alpha and sends it to us, which determines what is the new compressed information. Okay, so that is happening here. Now the trick in order to make this happen, so compressing this information is not helpful, because you cannot really tell the other one what the new compressed information is. So the only thing that the other person has, the verifier has, is this representation as vector g to the vector u. But this was the next trick. In order to do the recursion, they compress the generators as well. So we start with this known generators, and we take this to some power, which is from a challenge, and here's some other power to the power of alpha and alpha to the -1, and multiply them. And we get a new vector of generators with both parties know. So this is known. But what is not known is what's happening on the left side. And so you have to prove that this fits together. And for this, what we have is this is the product. This was the old commitment of U. GL to the U times GR to the U, which is the two vectors combined. So this is now a number, a small number. And so this this gives you new commitment for the recursion, where you go into this recursion for this new vector. So this is the commitment for this combination of new vector. But in order to prove that, you tell the other person that you commit to two values, which are these two values. I think this is VL, and this is VR. You commit to these two values and say, we have that, and you can later prove that there's no way to falsify these values, so that you can actually wiggle around with these values. So you have to send this, and then you can calculate that the new commitment fits to the old one. And then we go into the recursion, and we have a new commitment where we say that this is related to that one, and we have information of the exponent. And why is it working? because I get an exponent, a polynomial of 4 if I multiply this with alpha squared. So if I multiply this with alpha squared, so I have a polynomial of 4, and I have a value, a random value in this polynomial. And the only way to get to cheat is that I get maybe another value of this polynomial which have the same value. And here we get, and how many values do we have? And here we use the Schwarz-Sippel lemma, which says that you have any field and you have a polynomial of degree 4, then the probability to get another one is 4 divided, or d divided by s. And s is the whole set where you can pick off. So if you use that, then there are only 3 ways to make this differently. And we don't know this ahead of time. How to, and this, so this cannot be falsified by the protocol to make this commitment, because the other values are somewhere completely different, if they exist at all. Okay, so last time we already showed that this calculation works, that the soundness works, and that we can work with that, and the complexity is log n. For the zero knowledge, this is a complicated proof. So there is lecture notes from Justin Thaler where you can see that, or you can read the original paper. But I think here it's the best way to present the zero knowledge property of this hidden Petersen commitment. And this was a breakthrough. But now we have a vector, we can prove we know the vector. Now the next step was to do some operation. So if you have a vector, you can multiply a vector with another vector, in the commitment, which is an addition. So you get an addition for free. And if you get also the constant for free, because the verifier can, if a constant is known, can just take the generator to the power of the constant. The interesting thing was the folding product. Some kind of product, as we have seen before. Now, folding product or dot product is known as that you have 2 vectors and you have this addition of these values, which has a1 times b1 and so on. And the question was, is there an efficient proof to do this, that you have a multiplication operation of 2 vectors? And this was published in 2018 by Bunz et al. In this famous paper, which is called Bulletproofs and so on. Where do we have this citation here? It's here. So this paper here. And this is the trick that's working. So we commit. In the beginning, we commit to again. So G is a vector, H is a vector, U is a vector. So this is a product of G1 to the A1 and G2 to the A2 and so on. We start with that. We have again a recursive set where we check if n is equal. We just take the zero knowledge proof for multiplication, because then we are just 3 values. And when we do in principle the same thing, we take the A vector, split it, we take the B vector, split it, we construct new, we split also the generators, which are changed in the next round by using a challenge. So where's the challenge? The challenge is coming here. So the challenge is coming here, and here we construct new generators. But the for C, the U is untouched. So this doesn't change, this generator. Again, this is a trick, changing generator from one iteration to the next one by multiplying and applying operations. Of course, now there is a relationship between the original generator and the generator we have here. But as long as we combine generators which have no relation to each other and take care of that, then this is not a problem, as we have seen before, that there is a relationship between generators, because we combine unrelated generators. So both the verifier can compute a new commitment where we choose so where the prover will help us, help the verifier to show how to do that. So here it combines somehow the generators of a left side of A. And so we take GR to the AL and HL to the BR. So somehow left and right. Same here and switch it here. And this is needed so that the new commitment of this new somehow combined vector, as we have seen before, still holds. So the verifier has to verify that. We don't have to send it because both of them can compute it if the prover publishes L and R. And then we have a similar trick. Now X has the role of alpha. They have the left side times X and the right side times X to the minus 1. And here it's just vice versa. So that if you multiply both of them, what you get is that AL times BR, AL times BL, that the X and X to the minus 1 cancels, and also AI times to the BR. And then you have some leftover terms which will add it to your new value, which you also have to adjust. So you have to adjust C prime, and then you go into recursion. And this is just the algorithm. Of course, the proof that this is zero knowledge is hard. At least one can see that you have completeness, that this works. And soundness is now reduced to some kind of nearly zero soundness because of the Schwarz-Sippel lemma. There is a chance that by some chance the prover could guess a second root of this polynomial of degree 4, which might exist because of Schwarz-Sippel. But this is small and can be neglected, but it's not perfect soundness. Okay, so this is so why is this correct? So we can do the commitment. So first of all, let's look at what we're doing here. So we have a commit of G to the A to the B. Again, this is G1 to the A1 and G2 to the A2 and so on. And this goes into recursion like that. Here we have the formula for the recursion. Here this is the splitting left and right. And these are the two commitments which we need in order to help to show the correctness. So that here you can see that they don't have no X into it. So this also gives the verifier the chance with the challenge X to the square to show that this is true. Because otherwise the prover could come up with anything, but if a verifier says, here's an X, take it to the X power and see if it still holds. And here Schwarz-Sippel works because if you have random input for a polynomial, then we are only equal with extremely high probability if they are the same. So, okay, so that's the thing. So what we have to check is whether C prime is correct. Is it the correct commitment? And so this is all a copy on the right side. So is C prime correct? It's just a copy so that you can see that it works. So we have to compute the dot product of A prime and D prime. So A prime and B prime is given here. So you have to multiply this times this. And if you multiply this, you get AL times BL plus AR times BR, which is C, which is the original C. And then you have to here with residual terms, the AR times BL gets X to the minus 2. And then you get exactly the thing which is the new value C for the next round, which is not published, of course. So this is secret. That's what the prover has to do. And it also shows that prover has to know everything, has to know all experiments and so on. And the next question, is the commitment fitting to that? So because we do a commitment and the commitment is calculated without the secret information because the verifier has to do this. So for, the left side is again just a copy to see whether I have done it correctly. So we have to check whether the commitment for the recursion for the next round fits to G prime to the A prime and H prime to the B prime and U to the C prime. And So we plug it in. So this is the left side is given as the left L to the x squared times this one. And on the right side, if you plug it in, you see that the same trick is working. So this is G. So here we have G prime to the A prime. A prime was this term. Okay, so we have an x and x to the minus 1. So I already have the left side and the right side multiplied with exponents. You have the left side and right side. This is B prime, and this is H prime. So these are these ones. So we knew generators. I plugged them in, and when I do the multiplication, so these are now A prime and B prime, and this is C prime. And if you do this correctly, then you end up with GL to the AL here on this side. You have GR to the AR, and you have here HL to the BL and HL to the GA, which is the old commitment here, which you can reuse now. And we have some terms left over, which is this term. No, it's inside. Sorry, it's all inside this term. So we have some terms left over, which you see here, and you can see it here and here. So which will form this term here at this point, and here you can see that this fits. So that's so the commitment is so at least it's working in the sense that it's completeness. So we get down and we get the same commitment. Of course, that's not the zero knowledge proof. It's just this idea of making renewed commitment where we just reverse the sides and you adjust the C prime for it. That's a trick that the researchers haven't seen for decades, and which folds it together and forms a logarithmic zero knowledge proof. Now, n doesn't have to be a power of 2. You could add some columns to it. For this folding, it has to be always even to that it works, of course. And you can also easily modify to a hidden Petersen commitment, which is, just makes it more complicated, doesn't add anything. We can also use Fiat-Sharma heuristic, and this takes log n rounds and order of log n messages, and you can prove basically that you have two products of linear time, and you prove this logarithmic number of statements. So the companies you have seen, the soundness is not perfect. It's only with very high probability. And for zero knowledge, you have to read the original paper, because that's where most of the time is spent in order to show that this works. Now, that's not over here, because this is just some kind of special application. The question is, of course, we have seen that we can do arithmetic circuits and Boolean circuits in linear complexity. Can we do everything with logarithmic complexity? That's the next step. At some point you become greedy. It's not enough. You were happy with linear complexity. Now you want to have more. So what can we do? Now the idea is to combine many folding products. Is that we think of polynomials. So with the Schwarz-Zippel lemma, showing that two polynomials are the same can be done with one test. Give me a random number, we plug it in together, and then they're the same. So that's the idea. So we look at maybe large polynomials and prove that this is the same. And then we can describe it. And this is the idea how we want to do this. And I want to be here more concrete, because it's hard to see how it works. So one way is we could, for example, have lots of multiplications, like Ci is Ai times Bi. So this is called the Hadamard product, but it's basically just a bunch of parallel products. And what you could do is, so you are giving, now you have given now A, B, and C, which are all vectors, which is given by this commitment. And so with the CA, CB, CD, and you have some kind of generator G. And you can try to apply the same scheme, but with a slight modification. So just we go to this later on. So what we do is we just do it for all of the A and B, C in parallel. We compute the following, that we split the generators. We have the same structure as for the proof of that we know the coefficients of the bulletproof here. That's the same thing. But now we do something different, and this is happening here. At the beginning, the verifier sends me three variables, xa, xb, and xc. And this alpha is some power of that. So we don't need for the verifier to send me more alphas in each round. We just use your old one and take some power of it. So we take 1 over x to the power of n half. So if I go down, in every round I have a new challenge, which is given as several exponents, and this exponents ensures that I get automatically a polynomial. So now both of them compute the new commitment, and the rest is the same. So the secret, and that's the important information here, is now alpha times UL plus alpha to minus 1 of UR. And let's see what it means. So we have U, which is a vector, and we split it in UL, and we have UR. And so what we do is here we have alpha times UL. So this is alpha times the new vector, which is half a size, UL plus alpha to the minus 1 of UR. Now, if alpha is equal to x to n half, I get minus n half, I get UL times x to the n half plus this UL, which is UR times, so this is to the minus 1 half, and this is times x to the n half. So that means that each of the coefficients has a different exponent. And now if we follow it, so that basically all of these on the left side get the exponent of x to the minus n half, and all the right side gets exponent x to the n half. So if you do this recursively, so that means I multiply here everything with x to the power of minus n half and everything x to the power of n half. Now the next round this is folded, but inside the folding, these numbers still exist in the sum. So the next round I get x to the minus n to the fourth, x to the power of n to the fourth, x to the power of minus n to the fourth, and x to the power of n to the fourth. So what happens is that they get different exponents. Actually, I have to, because this I have to make x to the 8, so I have to adjust it so that they get different exponents in each round. And this continues until each of them has its own exponent, x to minus to the I, and this is x to the minus I plus 4, and so on. So we get each of these values get its own exponent because I folded this way. And so we can ensure that at the end we get a polynomial here of its exponents just automatically if we apply it in this way. So we fold it together in this way, and then we have three polynomials, and then we have to prove that these three polynomials somehow multiplied give a Hadamard product. And in order to prove that, we do the following trick. so that if you multiply one polynomial to the power of xi with another polynomial, so this is ai to the xi, and you multiply with another polynomial bi to the yi, so what you get, let's call this j, you get I and j of ai times bj of xi times yj, something like that. So you get a whole mixture of these things. But if we concentrate only on the polynomials which have the form x, y to the I, which are on the diagonal, then we get exactly the Hadamard product, ai times bi, and which is part of that. And we can prove that for certain generators, they are the same in logarithmic time. So we could take these polynomials out of this representation and show that, we can prove that here these coefficients, which have after multiplication have the same property, have the same one as here, and this way we could prove that this is the case. And we still need logarithmic numbers. The only thing of messages. The only thing which is a mess is that if you do a multiplication of these polynomials, you get quadratic many of terms, which we don't have to publish, but we still have to compute it. And that's how you could make a generalized Hadamard product. You see that the parallel product is more complicated than a folding product. And there's easier proof, not easier proofs, but smaller proofs. So the fuller proof is omitted because we don't have to finish this lecture this week. But for a more efficient zero-knowledge proof, which has linear number of operations and logarithmic number of messages, I have to refer to the original paper there. This was introduced the first time. Okay, so that's a bulletproof for the generalized, for the Hadamard product, where you have each of them. Of course, we can do similar things. This is an operation that we need for that. We can show a bulletproof for the equality of two vectors for different generators. If you look at this proof, it's the same thing that we have seen, that we know the coefficients of one generator. We have here we have u and v. Actually, this has to be w. It's a typo. We have public commitments here to two generators here. And so what we do here is we split these partitions again in parallel. We do everything in parallel here. We also split that one. And then we compute again these new commitments here. We have these new terms which fill up. These are completely individual. But since we do it for the same challenge, alpha, we end up with the same commitment in the next rounds. So this will be the same number in the next round, unless we are trying to cheat. And we do this recursively until in the first round we can prove that this is the same exponent with the first zero-knowledge proof that we have seen where we applied the Schnorr proof. So this also works. So we can actually transform from one generator to another generator, and we can do this in log and rounds. So we get lots of operation. We have parallel multiplication, we have parallel addition, and everything is in log n. So let's aim higher. How about matrix multiplication? So what is the problem here? So the problem here is that this is hidden. The red one thing is hidden. A and B is hidden. So we have m times A is some hidden vector B, plus this is public. The matrix is public, and this is also public. So what we want to prove that this is the same. And we also assume that m is somehow known at both sides. We don't have to transmit it in the beginning, because this is the largest chunk somehow. It's an m times n matrix of public no values. And we also assume that A and B are given as Petersen commitments and not available. So what we do is the following. So we have commitments for these n-dimensional vectors A, and this commitment here. And now we are using the components that we have already constructed to prove this step by step by multiple bullet proofs, because now we can go use the bullet proofs like building blocks, prove statement for statement. So for example, the easiest thing is, so we have this public information C and we want to add it into new vector. So I just take a new commitment for B prime, which is CB times this product of HI to the CI. Just multiply it. And now because CI is known, this is a public information, so everybody can compute it. We can multiply it. The prover knows the new secret, of course, but the verifier just knows, that's a new commitment. I don't even have to communicate for this because I know the coefficients and I can add it, and the prover does it in the same way. And when we get a new statement, and then we have a different problem, which is easier because when we just have to, where is it? Multiply. So where is it? Here. You just have to, no, this is not one. So you just have to M times A is C. So that's, yeah, this one. M times A is equal to B prime. Now, how can we prove that? Now we can use the Schwarz-Zippel trick. And what we do is we compute a folding product of a vector B and a vector which are all powers of xn, which gives one number. But this x here is now a challenge from a verifier. Now, you could say that you can compare two vectors by just making a polynomial and compare the polynomial. But because of Schwarz-Zippel, if the verifier gives me a challenge, then I just have to compare one point of these two polynomials. So that's what I do here. I want to produce a polynomial which characterizes the whole vector. And so that is happening here. This verifier sends a challenge, and then the prover commits to this polynomial, which is evaluated at this point. And so we get this is the new commitment. And this can be done by bullet proof of a dot product, something we have seen. So this takes log and time just to verify that this value, which is just a single value. So this is from GQ. GQ. This is an element of GQ. I just have an element of GQ. So that this value is representing the polynomial at the random position chosen by the verifier. So the right side is now one value. And another, later on, this is not a verifier sending the challenge, will be hash function with a predetermined value that we have to use. Okay, so what we do with the left side, because that's the right side, the left side also needs this thing, and the left side does the following. So we take the rows of the left side of this matrix multiplied by this challenge, which is still the same. And this is something you can do in public because the verifier gives you the xi. So you can make a polynomial. So you can multiply each row of that, and then you add it, and you end up with one value for first column, one value for the second column, and so on. So these are still vectors here. And then you have to multiply it, and it turns out that if you do it this way, the multiplication with A is again the dot product. So you do the dot product of the left side, and you get a polynomial characterizing MA of x, and you get a dot product on the other side, MA of x, so that's the left side, and you have the other side, you have B of x, which is, so this whole thing here is just, again, a value from GQ. A one value which characterizes the whole matrix product. And so by comparing these two values at the end, which are given by the commitments, you know that it's right, and the only thing that you need is a bullet proof that this dot product is the same as the right one, which we have seen is again log and messages. So what you have done is basically we folded this matrix operation with constant into a series of bullet proofs, which allows us to do matrix multiplication for some constant addition in log n number of messages. So where do we stop? Basically now, because we